All right, welcome back, everyone. That was a great session with Justin. Thank you very much, Justin, for answering all of our questions. I had a lot of my own answered, honestly, which is great. So, Justin is still on the chat on Slack. So, if you have any questions to him, definitely post them, and I'm sure it will help. But now with us we have Luis Beltran here. Hi, Luis.
Oh, hi, Alexander. How are you doing?
Good, good. We're awesome. We're so happy to have you. And you are calling in from the Czech Republic, right?
Yes, exactly. I have been here for the last 5 years. I'm from Mexico, but I am been studying and doing research here. And yeah, it's a great country to live in.
Awesome. And you're pursuing a PhD, is that correct?
Yes. It's a PhD in engineering informatics. The topic is actually deep learning and face recognition, face detection. So all about TensorFlow and Python, and yeah, that's my. I ate that for lunch.
Wow, so you're an expert on this topic. This is fascinating. That'd be great. And in addition, you're also a Microsoft MVP. That's correct, right?
Yes. In AI and developer technologies, I love, let's say, mobile applications. So that was my first one, and also I have been studying about MLNET and cognitive services, custom vision. So yeah, it's also helpful for acquiring experience in AI.
Oh, that's great. Well, I'm really excited about your talk, and I'm sure the audience will be as well. And as always, everyone, if you have any questions to Luis here, just post them either in the Slack channel or you can post them on Twitch and YouTube, and me and John are going to moderate them afterwards. But I don't want to take any of the time away from you, Luis. I'm really excited to hear this. I'm sure John is as well. So yeah, the floor is yours. Take it away.
Okay, thank you very much, Alexander and John. So also, thank you everyone for joining this presentation. I hope that during the next hour, you will learn a lot of things that maybe we can transfer this learning from this topic to you. So yeah, just contact me or send me any questions and I will do my best to answer them. So the topic today is transfer learning for deep learning, TensorFlow and ML.NET for the ML.NET Community Conference. I'm quite happy to be here. As I was saying, I live in Zlín, which is in Czech Republic, and I enjoy everything about mobile applications, especially with Microsoft technology, AI, and also cloud technology. Here in this slide, you have my email and also my Twitter handle. So feel free to contact me with anything about the topic or something related with mobile technology and artificial intelligence. So let's move into our topic. You know that in supervised learning scenarios of machine learning, we usually train models for specific tasks in a certain domain. For instance, detecting food, okay, this is a chocolate, this is a cake, this is, I don't know, some specific elements within a domain. And we assume that we are provided with labeled data for the same task and domain. So yeah, we have a file maybe which contains the information, okay, this image is a cake, this second image is a chocolate, and so on. So the idea is that, well, if there is another domain, we might have problems. We would not be able to recognize objects because, of course, this second domain has their own tasks, their own objects. So the task and domain of training and test data of our model A is the same. A task is the objective that our model aims to perform, such as recognizing objects in images. And the domain is where our data is coming from. For instance, images that you can easily find in a coffee shop or in a restaurant. So we usually train model A on this data set, and we expect to perform well. We use several algorithms until we reach, let's say, good performance or good high accuracy. But when we have this second domain, we require label that data of the same task or domain, so we can train a new model V. The supervised learning paradigm is not useful when we do not have sufficient or enough label data for this task or for the domain that we care in order to train a reliable model. So we cannot reuse an existing model as the labels between these two tasks are different or differ. Okay, so that's one problem. Second one is that, okay, training an image classification model from scratch usually requires setting thousands or even millions of parameters, quite enormous labeled training data, and of course, a vast amount of compute resources, especially if we are talking about the deep learning field, because we might need or require hundreds of GPU hours. Of course, we can provision cloud services which provide these high computational resources for us, but of course, there will also be a cost there or related. But usually, if we have enough data and also significant or relevant data, the performance of these models and the accuracy of what we are building will be better. But yes, we need high computational resources. So this is a second problem that we might encounter when we are training our data or when we are training some algorithms or using some algorithms. And then we have transfer learning. Transfer learning is a machine learning method where a model that we develop for a task can be reused as the starting point for a model on a secondary task. The basic idea is to use the knowledge that we gain while we solve the initial problem, and we can apply it to a different but related problem. Transfer learning, it's a popular approach in deep learning because we have several pre-trained models that we can use as the starting point on computer vision, but also on some other tasks such as natural language processing or even speech recognition. We might have used computational and time to train this initial model. Maybe it is a big, huge model. We might talk about neural network models, deep neural network models on these problems because we have or we require a lot of resources and skills. So in other words, transfer learning is an optimization that allows fast progress and also improved performance when modeling is the secondary task, when we need to generalize, yes, some of our initial labels. So just to compare traditional machine learning versus transfer learning, the traditional learning is an isolated task and occurs based on specific tasks, specific data sets, and training, separated models on them. The knowledge is not retained, but in transfer learning, we can leverage, we can take advantage of the knowledge that we gained before. And what is knowledge? Okay, it can be features, it can be weights, it can be layers, yes, from these previously trained models. and we can use them to train, yes, newer models and even tackle new problems. But we will not require high computational resources. We maybe have less data for these newer tasks. Think again that for our initial task, we require huge data sets, but for the second one, maybe we have less data. We can build a classifier, a custom classifier from there, okay? So how does it work? If we go, let's say, a bit deeper, in transfer learning, we first train a base network on a base dataset and task. Then we delete what is known as the loss output layer, which is the last layer that we usually is what we usually use, yes, to make predictions. Sorry. And replace it with a new loss output layer for general prediction. Okay, so there is a replacement there. This new loss output layer is fine-tuned, and it also helps to determine some penalizations from the label data and the predicted output. You will see that when we are talking about the demo, we will have this loss metric or statistic. And it is a good indicator or metric if our new model is it has a good accuracy or not. Okay. Then next, we will take this smaller data set for general labels and train it on the whole N layer neural network, or the last few layers, or maybe even the loss layer alone. By applying some transfer learning techniques, our output on the new network, maybe a convolutional neural network, will be able to identify general elements. Okay? So this is something important. Transfer learning only works in deep learning if the model features that we learn from the first task are general. Okay, more on that when I talk about the data sets. Yes, but usually in our secondary related problem, we will create generalizations. Okay, like maybe, for instance, at the beginning, we built a model that distinguishes between very specific types of or classes of dogs and cats and other animals. But in the secondary task, we would like to know, okay, if we have a cat, we have a dog, or we have some groups of animals. Okay. So yeah, that's important to know. We mentioned or we talked about pre-trained models. Of course, to solve the problem, we need a pre-trained model of the similar problem. Instead of creating a model from scratch and then require a lot of computation, a lot of features, yes, to solve a similar problem, we can use this starting point, this model that we train on the other problem, yes, as the starting point. And what kind of pre-trained models we might have? Okay, so first, maybe we have images like this that are very diverse, that they have differences in size, for instance. We might have pictures of dogs that can be any of the following that you can see in this slide. So you can see that in some of them, the area that where the dog is present is different. In some of them can occupy the whole image, and in others it's just a small fraction. Because of this huge variation in the location of the information, yes, of the relevant information, choosing some parameters such as the kernel size for convolutional operations is a tough or a difficult task. If we are talking about convolutional neural networks, we usually select a large kernel that is distributed globally. And well, a smaller kernel can also be useful if the information is distributed locally. One problem that we might find in convolutional neural networks is that if they are very deep, they might overfit, and it might be difficult to pass gradient values updates, for the entire network. So we have something which is called the Inception Network, which was an important milestone in the development of convolutional neural network classifiers. It was very complex, yes. It uses a lot of tricks to push performance in terms of speed and accuracy. So it is actually, or today we have the Inception version 4, yes, ResNet and GoogleNet that you might have heard of. Each version is an iterative improvement over a previous version. So understanding the upgrades can help us to build custom classifiers that are optimized in speed and accuracy. You can see in the left picture the initial or naive Inception module that performs convolutions on inputs with 3 different sizes of filters, 1 by 1, 3 by 3, or 5 by 5. And usually we use something called max pooling to create these pooling layers. So we select the highest number in each subset. Then the outputs are concatenated and sent to the next module. To make it cheaper, to overcome this problem that we might have computationally expensive deep neural networks, the creators of the Inception network limit the input channels by adding a 1 by 1 convolution before the rest, before the 3 by 3 and 5 by 5 convolutions. So this might not make sense, but actually the reduced number of input channels help. And yeah, also the dimensionality was reduced. So after using this Inception, a neural network architecture was built, and this is popularly known as GoogleNet or Inception version 1, which we are going to use for this demo or for this scenario. So yeah, you can see the ImageNet, which is a data set which contains several classes. We have labels, as we were talking about supervised learning. So we have the labels for some of our classes. Okay, we have a Kit Fox, English Setters, Siberian Husky, and so on. And you can see some examples of these tags or pictures. Okay. So of course, we have millions of or thousands of images. So you can imagine that creating an image classifier to let's say predict or detect what is happening in new images. Yeah, this will take training a model or training a network for this takes a lot of time. Okay, but what if we would like to simply identify, I am talking now of a second, let's say, task, yes. What if we would like to determine generalizations? Okay, we have a food here, we have a toy. We don't want to say, okay, this is a teddy bear or this is a pizza. No, we just want to group, okay, we have food, we have toys, or we have some kitchen items or appliances there. Yes, so that's where transfer learning enters, okay? The Inception model has already been pre-trained on thousands of images. So we can leverage, we can gain, yes, learn from this previous experience to build this new, let's say, custom model for us, transferring the ability to recognize and classify the images for this specific case, specific, but in the end, general, let's say, cases. Okay, I want to say specific because it's only these three cases or these three categories. Okay, a second option, of course, is to use custom vision. Custom vision is part of the cognitive services, and with custom vision, you can also create an image classifier. In the end, you will have you can train by submitting images in the portal or also by using the SDK. You can create the image classifier, which you can export as a TensorFlow model. And this can also be your starting point for the transfer learning. Okay. So now let's talk about transfer learning in ML.NET. So we are now to the point that we have an Inception model, or we have a TensorFlow model. You know, you have your ND file, TensorFlow, which you obtain from previous training, okay, by you or by some company. So now we have our data, and you can see that this is a quite a small data set. You have 8 images, 8 pictures there. You have your labels, your tags for your new task. Okay. You have, okay, some broccoli that you will say, okay, these are food, these are toys, these are examples of appliances. Okay. And you have your tags. In your project, okay, you will just get some references to your files, okay? And I also have another picture, which is not listed here, but of course, I am using this one for testing, yes, for evaluation. Yeah, I could have also used this toaster tree, which is not included in the inputs, but okay. Yes, and you can see here our TensorFlow model, okay? Then we have our input data model. We have the image path and the label. This is just the structure that our new model will, let's say, use, okay? We have the image file and also the tag or the label. You saw it there. We also have the prediction model, which contains the first two properties, because you can see that it is using inheritance from this class. And also we have an array of scores. Let's say every new tag will have some probability. Of course, the top one is the one that we are prompting to the user, which is, let's say, the one that the model detected that it is. And yeah, the predicted label value. We also have these inception settings. Actually, this is quite important. This is from our TensorFlow file. We obtain this, the size, the height, and width, yes, from our structure, from our data. Yes. So it is important that you analyze a model, your file, your TensorFlow model, maybe with Netron or with other tool, to determine if the size is correct. For custom vision, the size is 227, I believe, or yeah, I think 2027. Because if it is not correct, you will get an error that one size was expected. I can tell you where. So it is important to know this in advance. And yeah, also the mean, the scale, and so on. So this is where the transfer learning actually is happening. This is one of the important or key elements, the multiclass classification, which is a supervised machine learning that we can use to predict categories of instances of data. In machine learning, in ML.NET, you have the following training algorithms. You have multinomial logistic regression algorithm, which is the one that we are going to use. There is a naive Bayes, there is one versus, and there are others. There is also image classification, which expects, let's say, images rather than the image paths. That's another one that you can use. But for all these algorithms, you need the inputs and outputs. The inputs are labeled and feature columns, and the outputs are the score and predicted label, which actually are in accordance to what we mentioned here. Okay, the input data model and also the image prediction model. Okay, so that's there. And we are going to add this machine learning task, let's say our algorithm for our secondary task in the model pipeline. So, okay, this is quite a lot of information, but let's dig it little by little. So the ML.NET model pipeline is a chain of estimators. Actually, we saw some of this in the workshop yesterday. So the pipeline, these estimators create a pipeline for the model, train the pipeline to produce the new ML.NET model. And we can also evaluate the model against on-scene tested data. So the first part is to add the estimators to the model, to load the information, resize, and extract the pixels from the image data. So you can see here, we firstly load the images from our image folders, only the 8 ones that we had. Then we resize it to the image width and height that we specified. And we also extract the pixels, okay, that are for our new training, okay. So of course the image needs to be processed in the format that the TensorFlow model expects. So that's what we are using, that dimensions. Then we add the estimator to load the TensorFlow model. You can see it here, load TensorFlow model. And Inception TensorFlow model, it's the reference to our file, okay? So we process the vectors of the pixels, yes? We apply the inputs to a deep learning model, and generating the output is referred as scoring, yes, this scoring part. That's basically for the inference or for the prediction. In this case, we want to use all the layers except the last one, because the last one makes the inference. The output of the previous to last layer is known as softmax 2 reactivation. If we check the model in Neutron, which I think I have it here, yes. You can see this name here. Okay. Let me show you. Yes. We have it here. Okay. Yes. So that's the name that we use. Okay. Softmax 2 pre-activation. It's here. It's the previous layer. Okay. And this is, of course, our file, Inception Graph PV. And the rest is just mapping the string labels in the training data to the integer key values. Also, well, using the labels and also adding the prediction or predicted label value. And yeah, basically that's it. Of course, the code is not executed here. I mean, we are just preparing the estimator. It is actually performed, or all these tasks, all this training is performed when we indicate, okay, let's now train the model. So as an input, we take, of course, our tags. Yes, we load the text from the text file. And we use the fit model to actually perform the training by applying the pipeline. Okay. And of course, you can use or you can get this information from databases, not only from text files, even from memory. You can obtain from enumerables and so on. Okay, we transform the test data. You can see it's similar. We also use the iData view, but now it's for the test part. We transform to get the predictions. Yes, and we evaluate the prediction set. Yes, and I mentioned you, or I told you that we would have this log loss, and also, okay, the log loss is the general one, and we can also check, okay, for each category, for each class, what is the performance or the accuracy in the term of the log loss, okay, logarithmic loss. You would like these values to be closer to 0. If it is higher or closer to 1, yeah, you have errors there. And okay, the last part is to run the application. So basically, we just call this generate model and we classify. Yes. Okay, so I can show you. Okay, this is the full code that I just explained to you. And let's run. Of course, as I told you, to create this classifier that was based in thousands of images, you can imagine how much time it took. But now just check how much time it takes to create a classifier for these 3 classes or categories. So it is running now. This is the picture or the image that I'm going to analyze. Okay, I should not open it like this. Okay, just give me a second. So this is going, it's analyzed, and yeah, it was detected as an appliance. Yes, and you can see, okay, the log loss is 6%, 8%. Okay, so yeah, we could use more maybe images, or we can tune the parameters to decrease these values even more. And yeah, basically that's it. As I said, well, we could use other algorithms here in the check. Yeah, in these trainers. Yeah, we could use naive AEs or one versus all. Yeah, but each of them have their own requirements. And yeah, this is a way to create the transfer learning part with ML.NET. So you can compare, for instance, what we learned in the workshop yesterday, that we create classifiers or regression models but we add the pipeline. We add in the pipeline more, let's say, steps. We part or we start with this TensorFlow model, and the rest is just taking this knowledge to create your custom classifier. Basically, that's the main idea behind it. And okay, well, yeah, just to finish this part, why you should care about transfer learning. Well, according to Mr. Andrew, transfer learning will become a key driver of machine learning success in industry. You can see some, let's say, predictions there, and transfer learning is set as key element here. So yeah, that's it. I would like to know if there are some questions about it. If yeah, what are people saying?
Yeah, thanks, Luis. It's a great talk. Let's see. I think there's only one question I see, and someone's wondering if the code that you have, is that on GitHub or somewhere that they can look at it?
Yeah, I can share it on my GitHub. It is actually based on the demo that we can find on the docs, but yeah, I can share my GitHub. I have not uploaded it there, but of course I can share it. Just I think I can add my address. It's icebeam7, but give me a second. Oh yeah, it is this. I will add it in the chat later, but yeah, I can post it in the next hour.
Okay, cool.
Yes.
I think that's all. Praveen is asking what all hyperparameters that would be configurable.
Parameters that would be configurable. Okay. Yes. Well, for instance, here in the classifier, you can check enforce non-negativity if you don't have negative classes or history size, or you can even have weight columns, yes, or regularization or optimization tolerance. In each of your classifiers, you might have several parameters that you can tune there. So this could be a starting point to try or to compare several of your new trainings.
Yeah, that's like quite a few things you can experiment with there.
Yes, yes, yes. As you can see, most of them are optional, but we use only a couple of them, the column names and features.
Cool. There's another one here. What type of projects are you excited about trying next that use deep learning and ML.NET?
Well, that's a very good question. Well, my research is mainly about face detection and also emotion recognition. So I'm working mostly on that field. I usually, let's say, working on how to optimize when you have to distinguish between two emotions that are similar, such as sadness and also like indifference. Because in sadness you are like this, but in indifference you are like right. But still, in some of the research or in some of the let's say algorithms, the results are confusing between these two emotions. So I'm always working or finding new research. Right now, I am experimenting with the activation function, and I am learning about exponential. There is ReLU, rectified linear unit, but in new research or in new papers, you can see that the exponential linear unit is performing or getting a much better performance. So I am working on that part. Yeah, I wonder if I can do the same with MLNet. I might try and see.
Yeah, that would be interesting.
Yes.
Let's see. Have you used transfer learning in any other of your projects? And where, if you have, has it worked well?
Well, yes, but let's say not with ML.NET. I mean, with TensorFlow and also with some Python code. Yes, basically actually it's similar. Like we use ResNet or other data sources and also other models that have been trained. The Inception version 3, version 4 maybe, and we use it to categorize different, let's say, classes or different sets. Also, well, it was for learning, also for research, but yeah, not yet in any, let's say, practical or some like production, let's say, task yet. But it's part of the research, always learning and reading about newer technologies.
Cool.
Yeah, if some of you are interested, yeah, I can share some of the work. Just drop me an email, and yeah, I would be glad to share and collaborate, definitely.
Yeah. Let's see. Another one, since your research is mostly in the Python and TensorFlow, what are the main things that you miss from ML.NET in comparison with those other tools?
Okay, yeah, that's an interesting question because, well, ML.NET, I really like it because I am a C# developer before coming, let's say, to the artificial intelligence field. I was developing a C# application. I'm still developing because I am mobile. So maybe one thing that I miss, but there is a workaround. One thing that I miss is to export, let's say, the model as a TensorFlow model. I don't know if this makes sense. Of course, we can convert it to, as we checked yesterday in the workshop, as a zip file, and then we can put it on a web API so our applications can consume it. And it is possible in mobile applications to use this TensorFlow model directly to create image classifiers or even object detection capabilities. But to, let's say, directly integrate this model that we created here directly is not possible. I think maybe I'm wrong, but I cannot, let's say, export or create a TensorFlow model from here to put it directly on my mobile application. So I need to export the zip or the model, the ML model, yes, MLNet model, and put it somewhere and use it like, let's say, as a bridge here. So yeah, that's the workaround, but it's still possible, let's say. And I have not explored all the algorithms here that are present for the classification or for other tasks. So I don't know if, for instance, we can add our own, or if this part could be open source, maybe like the ML.NET team can benefit from algorithms that are developed from the open source community or from the research community. I don't know if that is possible, if we can bring our own. So, but that's also interesting for me because that's another thing that I can learn.
Yeah, definitely. So I guess one more quick question. Do you know of any data augmentation techniques in ML.NET, if there are any available.
Wow. Yeah, to be honest, I have not explored that part. That augmented reality, it's of course interesting. It's one of the topics. Well, one friend is organizing a Xamarin event, and that was one of the topics, augmented reality. That was one of the topics that people, let's say, requested. So yeah, I see. But I know that there are some libraries that you can use, let's say, outside, but not in ML.NET. I mean, I don't know if in ML.NET could be possible, or if that's from different fields. To be honest, I'm not sure about it. And maybe someone from the team can respond that, or could help me with that. But definitely, it's an interesting topic that is part of, let's say, the future or even the present.
Yeah, it will be interesting. I'm not sure myself, so it might be something we would need to open an issue and ask a question on.
Yes.
Luis, thanks for your presentation. It was great. Thanks for coming on.
Thank you for joining. I'm quite happy to be part of the event, and I will be also in the Slack community chat answering more questions if you have, or if you want to talk to chat, I will be there. Thank you all for joining, and good luck with your research. As I said, if you want to collaborate, my email is there. And have a nice day, everyone. And thank you, all of you, for organizing this.
Thanks for being here.
Goodbye.